You know, you see it every day on the news or on your phone, the weather map. It's got all those squiggly lines, big letters, and colorful symbols that tell this amazing story. And in the next few minutes, we're going to crack that code together. Yeah, if this whole thing looks like a big jumble of abstract art to you, trust me, you are not alone. But by the end of this, you'll be able to decode it like a pro. So let's dive right in. All right, first up, let's get into cracking the weather code. See, a weather map is so much more than just a snapshot of what's happening right now. It's actually a powerful predictive model. It helps us see all these complex things happening in the atmosphere, so meteorologists don't just know what the weather is, but where it's headed next. Okay, on to section 2, the atmosphere's moving parts. To really understand what the map is showing us, we first have to get a handle on the huge forces that actually create weather in the first place. And this right here, this is the key to everything. The sun heats the earth, but it does it unevenly. And that one simple fact is the engine for the entire system. It gets these massive bodies of air moving, creating literally everything we call weather. So, the main characters in this whole atmospheric story are what we call air masses. Just think of them as these giant, invisible bubbles of air, and each one has its own personality. You know, some are cold and dry, others are warm and humid, and the real weather action happens where these different characters meet. Now, here is a huge piece of the prediction puzzle. Thanks to the Earth's rotation, there are these massive currents of air high up, called the jet stream, and they tend to push weather systems across the United States from west to east. It's why the weather in, say, Colorado today is often a pretty good preview of the weather in Kansas tomorrow. This is really the foundation of forecasting. All right, section 3 is all about decoding pressure in fronts. Think of this part as learning the alphabet of our new language. So much of what you see on a weather map boils down to two main ideas: high pressure and low pressure. High pressure is kind of like a hill of cool, heavy air that sinks down and spreads out. Low pressure, on the other hand, is like a valley of warmer, lighter air that's rising up. And as you can probably guess, that rising air is where all the action happens. So when you see this big blue H on the map, I want you to think happy weather. This is that cooler air sinking down. And because the air is spreading out, it actually stops clouds from forming. That usually gives us clear skies and pretty calm conditions. And on the flip side, you've got the red L. For this one, think lousy weather. This is where that warmer, lighter air is rising, and as it rises, it cools off and condenses into clouds and, you guessed it, precipitation. And because the Earth is spinning, it's something called the Coriolis effect, these low-pressure systems spin counterclockwise up here in the northern hemisphere. They're basically breeding grounds for storms. So what happens when these different air masses, pushed around by those pressure systems, actually run into each other? Well, you get a front. And I love this analogy. Think of it as a weather battle line, because that's where the most dramatic changes always happen. These lines, the ones with the little bumps and spikes on them, those are your fronts. There are 4 main types: cold, warm, stationary, and occluded. And each one tells a completely different story about the battle that's happening in the sky. So let's see them in action. Next up, section 4, from lines to rain clouds. Now we're going to see what happens when these fronts start making the weather you can actually see and feel. Okay, check out the drama of a cold front. That line with the blue triangles, that's a cold air mass acting like a bulldozer. It just aggressively plows forward and shoves that warmer, lighter air straight up into the atmosphere. This really fast vertical lift is what creates those huge, angry-looking cumulonimbus clouds that can unleash thunderstorms and heavy rain. Now, a warm front, that's the red line with the little semicircles, is a much gentler story. Here, the warm air doesn't get shoved around. Instead, it just gracefully glides up and over the cooler, denser air that's already there. This slower, more gradual lift usually forms these wide blankets of stratus clouds that bring a steady, lighter rain, often for a much longer time. And just real quick, the other two. A stationary front is exactly what it sounds like. It's a stalemate. Neither air mass can move the other one, and this can lead to days of just gloomy, overcast, wet weather. An occluded front is a bit more complex. That's when a faster cold front actually catches up to and overtakes a warm front, and that can create a real mix of unpredictable weather. And finally, section 5, forecasting your world. Now that we've totally cracked the code, let's see how this knowledge becomes a real-world superpower. So you might be wondering, where does all this information even come from?
Well, it is definitely not guesswork. Meteorologists use a whole army of scientific tools to gather hard data. They use barometers for pressure, anemometers for wind, hygrometers for humidity, you name it. This constant stream of data is what powers the incredible predictive models we see as weather maps.
So, why does any of this really matter? Well, because being able to read this secret language has some seriously powerful real world uses. It helps you decide if you should have that picnic this weekend. It helps farmers protect their crops. It keeps pilots and drivers safe. And in serious situations, it helps whole communities prepare for severe weather. It's not just trivia, it's practical, powerful knowledge. So, the next time you look at a weather map, don't see a secret language. See a story of pressure, of colliding air masses, and of the incredible, dynamic atmosphere that's right above your head. And the best part is, you now have the tools to read it. And that leaves us with one final thought. I mean, we've come so far, from simple barometers to these advanced satellite radars that can literally see moisture in the air. As that technology keeps getting better and better, do you think we'll ever reach a point where we can perfectly predict the weather with 100% certainty? Or will the atmosphere always have a few surprises up its sleeve for us?